Tiny. Okay, so hello everyone. We have Eduardo da Silva Ribeiro. He's a new student, PhD student in PUCB. I put in the email, it was UNAB, but was my mistake. I'm sorry for that. So he's gonna talk about some research that he did on his bachelor in Brazil, and it's about graphene, Dirac fermions into it. So Eduardo, you have about 50 minutes.
Okay, thank you, Felipe. Thank you for the invitation. So my idea here is to present some basic stuff about the electronic structure of graphene, especially low energy behavior of the electronic excitations in graphene. So my main plan, little outline of what I will talk is make a little historical and technical introduction about that. Then discuss a little about the structure of graphene and its electronic structure, the effect of magnetic fields in graphene, and the general relation between gauge fields and curvature in graphene, and in the end, make some little remarks. So, okay, let us begin. The first thing about graphene, some historical note, it was first theoretically described by Phil Russell Wallace in 1947. The idea he was trying to study electronic properties of graphite, and in the end he imagined these 2D sheets of carbon atoms to describe its electronic properties. So sometime later, Hans Peter Bowen coined the name graphene while studying extremely thin flakes of graphite. So in a certain way, he was the first person to synthesize graphene. Even Andrei Geim and Konstantin Novoselov credit him for discovering graphene. So in 1984, Gordon Semenov, David DiVincenzo, and Eugene Melli, they predicted the emergence of Dirac fermions in low energy excitations, electronic excitations in graphene. And in the end, I think it's what most people already know is that it was first isolated and characterized in 2004 by Andrei and Konstantin Novoselov. And this gave them the Nobel Prize of 2010, if I'm not wrong. So, since the discovery of Gain of Novoselov, I think graphene has become one of the most hyped topics in theoretical physics and experimental physics. So one important thing to move on here is to know what is graphene. So basically graphene is an allotrope of carbon. And we know carbon has a lot of allotropes. Here we have two examples. Here is a diamond. It has a tetrahedron structure, crystal structure, if I'm not mistaken. And here we have graphite, which has a very different structure, which is basically a lot of sheets of monatomic, of one atom of thick, stacked one over another, and which are bound by means of van der Waals interaction. So graphene itself, it's one of the single layers of graphite in which the atoms will be organized in a honeycomb lattice, which is basically an hexagonal lattice. So here it's a 3D model of graphene of the honeycomb lattice. And this is a scanning transmission electron microscope image of graphene. So we can see it indeed has an hexagonal lattice. Well, what is the structure of graphene, the physical structure of graphene? So the first thing is that carbon has this electronic configuration. So we have 4 valence electrons, specifically the 2s2 and 2p2 electrons. And what happened in the specific case of graphene is the following. So we will have 2 electrons in the 2s orbital. These electrons will be completely filling this orbital. And we will have 2 electrons in the p orbital, one in px and one in py, and another electron in the pz orbital. These are all the 4 valence electrons of carbon. In the case of graphene, there will be a hybridization between these, the s and p orbitals. So we went with an orbital that calls sp2, which have 1 electron in each of its places. And there will be another orbital, the pz orbital, with 1 electron alone there. One important thing to know that this hybridization process is very important in structure formed by carbon. For example, the sp1 hybridization is important to structures in organic chemistry, whilst the sp3 hybridization, it's the hybridization that it's formed in diamonds. So this is all about the allotropes of carbon are made. So in the end, we will end up with something like that. The sp2 orbitals will merge itself to form these hexagonal structures, and the pz orbitals that are free, so let's say that way, they will hybridize themselves and form one big delocalized orbital that goes over all the structure of graphene. So this is pretty much like we have free electrons in a metal, for example, with the difference that graphene is not a metal, it's a semi-metal. So the crystallographic structure of graphene is basically about that. The important thing is that the honeycomb lattice, or hexagonal lattice if you prefer, it's not a Bravais lattice. So we need to split this hexagonal structure into 2 sublattices, A and B, 2 triangular sublattices that I'm calling A and B here, that will be generated by these 2 vectors, which are basically these 2 vectors here. Besides that, we have the nearest neighborhood vectors, which are these deltas here. So basically the lattice vector, it connects with the next atom, which is within the sublattice. And the next neighborhood vector, it connects the atom with the first neighborhood it has, which is always of the older sublattice. And here we have, for finite systems, real systems of graphene, we have basically 2 kinds of terminations of boundary conditions. Right? The first one is this green termination here, which is called zigzag. And the another is this red termination here, which is called armchair. An important remark here is that the zigzag condition is much more realistic in the sense that a generic termination for graphene will be most of this form. This is a very specific kind of termination that I think it's more of something artificial you can create. So we also have here the first Brillouin zone, which will be generated by these 2 vectors. Here we have the symmetry points of the Brillouin zone. We are really interested here in this K point, in this K prime point, which we'll see what they are. So before talking about the electronic structure, I need to make a very brief discussion of tight binding models. So the idea of a tight binding model is to make an approximation based on the superpositions of the wave function of isolated atoms. So in order to this work, we need to assume that the electrons are tightly bound to the atoms in the lattice. So we can write the Hamiltonian within this approximation in second quantization. It will be something like that. So basically, what this Hamiltonian will be making is if we have some electron in a lattice site R, given by its letter R, and within some orbital with index lambda, the only process that can occur in this physical system is the jump of this electron in this configuration to the jump to another configuration in another place or lattice site that I'm calling R prime within an orbital lambda prime. So basically, this will have an energy associated, which is the energy here, which is called the hopping energy. So in the case of graphene, we will consider here only near neighborhoods, the first neighborhoods as of possible for this hopping I told. And we also have only one orbital, which is the PZ orbital. The other orbitals are not relevant for the electronic properties. So in the end, our Hamiltonian will have this phase here. So we have one electron in the sublattice A in the position R, and these electrons can jump. These electrons can jump to one of its neighbors, which will be in the position R plus delta. If you remember that delta is the vector that connects one atom to one of its three near neighbors. And it will be in the sublattice P. In this case, the hopping energy will be just a constant since it's isotropic. And so starting from this Hamiltonian, we can use the block theorem to make a sort of Fourier decomposition of these operators. And in the end, we end up with something like that we can make look even better to generalize. So we can introduce some a spinor structure of this sort. Yes?
Eduardo, I wanted to ask you a question because I'm not familiar with I'm not, of course, not familiar with the system. But how realistic is the approximation that you are making only considering near neighbors? I mean,
yeah.
Are you aware of, do you know any other modeling of the same system that considers interactions of, I mean...
Well, you can add interactions, but analytically it's very difficult to treat these interactions. So most of these studies will be made using numerical methods, and for that, the tight binding model is very good.
Right.
You cannot add.
So it's precise to account for experimental data or something?
Yes.
Okay.
And you can also add other types. Here we are considering only hopping between the first neighbors. You can add hopping between second neighbors, third neighbors.
Perfect. Thank you.
Right. So, okay. So we have this Hamiltonian here in the end after making this Fourier transform. So we can solve the eigenvalues of it, introducing this spinor structure here. So we will have one component for the A sublattice and another component for B sublattice. And we can write the Hamiltonian in this way. So from here, it's easy to diagonalize it. And we find that the energy eigenvalues will be this will be this guy here. So we have basically two bands, one positive above the Fermi level, and another negative below the Fermi level. So it has this form here. It's basically, you can say it's a little ghost here, but the important thing here is that we have 6 points where the upper band touches the lower band. So the lower band is the valence band. Yes.
El profe me invitó a una charla. El Mari.
Sorry, can you repeat?
No, it's just someone that left the microphone open.
Ah, okay.
I made it.
Okay. So, well, basically we have 6 points here where the upper band, which is the conduction band, and the lower band, which is the valence band, touches itself. So we have 6 points where there are 0 points. If you look closer to these points, you will see that near the Fermi level, it's the 0 value for energy, they become a linear dispersion. So of these 6 points, only 2 of them are non-equivalent. We can see this by using the symmetries of the honeycomb lattice, which are these 2 diametral opposed positions, which I'm calling K and K prime. These are called Dirac points or Dirac cones, more specifically for this conical structure here. And here it's where we will focus from now on. It's where the interesting thing here is for us happens. So what we want to study is the low energy physics close to this region of the Dirac cones. So the idea here is to make a Taylor expansion for our Hamiltonian. So we can write our wave vector in this way with K is way smaller than K, with Q way smaller than K. It's of the inverse of the lattice spacing, which implies that the Q times the lattice spacing is way smaller than 1. So if we take these functions in the Hamiltonian and Taylor expand them, we find something like that, which I can use some tricks and write in this form here, the Hamiltonian in the end. I may be clear here. What I'm Taylor expanding is this Hamiltonian in the middle, which is called the Bloch Hamiltonian. So it will have this form here. And we define the Fermi velocity as this constant. And we are introducing 2 degrees of freedom here. The first one is the tau, which is related to the Dirac point that we have, which is called valley. So for the valley K, we have tau equals 1. And for the valley K prime, we have tau equals -1. And here sigma, it's another degree of freedom, which is related to the sublattice, the 2 sublattices we have, A and B. So in the end, the sublattice act in the low energy limit as some kind of pseudo spin. So the energy dispersion for this Hamiltonian is just a linear relation. And here we can start to see some interesting things. First, it's independent of the value of tau. And lambda here, it's our band index, which means that we have +1 for the conduction band and -1 for the valence band. But what we have here is a linear dispersion. And you may recall that in Dirac fermions have linear energy dispersion. So in fact, we can verify that this is the low energy limit, since we have this formula for the energy we obtained, and the Q times A way smaller than 1 implies that E is way smaller than the hopping energy. So indeed, we are restricting ourselves to the neighborhood of the Dirac cones. So we have another trick here. We can introduce a Dirac force spinner for this Hamiltonian. It's important to note that in the two later components, there are sublattices B and A they change the position. And we can write the Hamiltonian in this form. And here we can compare it with the Dirac Hamiltonian, which we all know. So basically, we have that low energy electronic excitations in graphene will behave exactly like 2D massless Dirac fermions with two flavors instead of just one. The first one is the valley pseudo spin, or valley iso spin, if you prefer, which is represented by the Pauli matrix tau Z. And the sublattice isospin, which is represented by the sigma Pauli matrix. So, okay, that's very, very interesting indeed, especially because it's massless particles. And indeed, this is one of the reasons why you can see that graphene has a very good electroconductivity, for example. And this will have another interesting effect, that the same way in high energy physics, we can define a pseudo-helicity for our pseudo-chirality, since we have massless particles of our quasi-particles in this way, which is, again, the projection of the spin, of the pseudo-spin, of lattice pseudo-spin in our direction of propagation. And since the helicity operator in the Hamiltonian commutes, we can write the Hamiltonian just in terms of the helicity operator. And consequently, the energy spectrum will have this form, which basically it will depend in the helicity of the quasi-particles. So by means of that, we can see that the band index will be completely determined by the valleys isospin and the helicity, because we can compare them. If we compare this with our other dispersion, we can see that lambda will be equals to tau versus eta. So in the K valley, we will have the quasi-particles in the valence, in the conduction band. We'll have positive helicity, and in the sorry, I think I say the wrong name. This is the conduction band. They will need to have positive helicity, and this is the valence band. And the quasi-particles will need to have a negative helicity. In the K valley, on the other hand, since we have a different sign, we have the inverse situation here. The electrons in the K prime valley in the conduction band will have negative helicity, and the electrons in the valence band will have positive helicity. So this is important because basically we are restricting the states the quasi-particles may have in each valley. And this, for example, prevents the backscattering of the quasi-particles in the case, for example, of electrical current in the system. So backscattering is one of the most important factors that contribute to electrical resistivity. And we are basically saying that we can't have backscattering. So again, we have a very good signal that graphene has a very good electroresistivity. So now I want to discuss the effects of what happens when you apply magnetic fields in graphene. Sorry. So in order to account to the effects of magnetic fields, we will need to make the Pyro substitution, which is the name of the minimal coupling for condensing matter systems. So basically, we will exchange our momentum, or in our case, our pseudo momentum, by the momentum minus the coupling with the potential vector. So this substitution will be valid as long as this a tilde here is minor, it's very smaller, is smaller than the magnetic length of the system. Okay, this a tilde here is basically the lattice space. So what's the norm of the lattice vectors that generate the lattice vectors? So as long as this, good way of, so as long as this is happening, we can make the substitution. So for simplicity, I will use the Landau gauge here. But using Landau gauge, basically our Hamiltonian will have this form, which I can obtain the spectrum by using some tricks. It's basically introduce convenient momentum operators, and from them that introduce annihilation and creation operators. But by doing that, we can see that the spectrum of this Hamiltonian will be very different from the case where we had no magnetic field at all. So the thing here is that our energy levels will be quantized. And they are quantized in a very specific way depending on the site they are. So for example, if n equals 0, we see that for the k value A sublattice and the k prime value in B sublattice, we have 0 energy levels. And for the k value B sublattice and k prime A sublattice, we don't have 0 energy levels. So this is interesting. This is important for what we'll see soon next. But one other important thing here, one thing that very important that I forgot to mention. This kind of quantization of the energy levels in the presence of a magnetic field is called the Landau levels. So this here are the Landau levels itself, and they are very important from the quantum Hall effect. The basic idea here is that when we consider a magnetic field in the system, we will be breaking translational symmetry in some direction. In the case of I did, which using the Landau gauge, I broke in the x direction, but I could choose to break in the y direction. It doesn't make difference. The important thing here is that we are breaking translational symmetry in one direction. So in the end, this means that we are considering a finite system, at least in one direction. And this leads to the formation of side states. So here, for example, I have a graphic of the Landau levels for, maybe I should put that, but it's basically, I forgot the word, but a sheet of graphene that is infinite in the y direction. Oh, sorry, it's infinite in the x direction and is finite in the y direction. And here the color is basically the projection in the
sort of strip or ribbon.
Yes, ribbon. Thanks. It's basically a ribbon of graphene that's infinite in one direction, and of course in the other it's finite. But what is interesting here is these are the Landau levels with the projection in the position operator, especially in the Y operator. So we can have that in the middle, we have some states that are fixed in the bulk, in the middle of the ribbon. But when we come to the bar, these kind of states here, they are localized in the boundaries of the ribbon. And more interesting, there is a splitting of the Landau levels when you come close to the borders. So basically, what we're making is making like a potential confining of the possible states you may have. So basically, these states are very important here for quantum Hall effect, because the way we calculate Hall conductivity, I won't dive into details because this is a complicated issue and it will have a specific presentation only for that. But the way we calculate Hall conductivity is using the Chern number. This is the quantum of conductivity, and this is the Chern number. And this is the definition of the Chern number. It's basically an integral of the Berry curvature over the Brillouin zone. But basically what the Chern number is counting is the number of edge states. The Chern number needs to be an integer, and this integer will be the number of edge states that we have in the system. So if you include spin degeneracy, which we are not considering so far, but to have the total conductivity, if we include that, if we set the chemical potential above the nth Landau level, we can see that we have 2 times 2n plus 1 edge modes. So basically we have this number of possible channels to conduct current. And this is basically the Chern number. It's what we will obtain if we calculate it directly. So in the end, the Hall conductivity for graphene will be this here, which means, so what's important here, it's the quantized conductivity. And this is what we call the quantum Hall effect. Basically, it's the quantization of the Hall conductivity. Well, of course, this is, we don't need to stop that by analyzing the effects of gauge fields in the graphene. And in fact, there is a more general connection between gauge fields and curvature in graphene. So the main thing is that if you have a substrate for your graphene sample, or you apply some kind of strain field to your graphene, you can make it become curved. And the interesting thing here is that we can model the low energy excitations, which are basically Dirac fermions, using quantum field theory and curved spacetime formalism. This to say that we basically say that we have now fermions in a curved manifold. So what we will use for that is the Dirac equation in curved spacetime. So it will be not that Hamiltonian we saw first. It's a different Hamiltonian with some different things here. So the first thing is that the Dirac matrix, they don't more have they have a different commutation relation, anti-commutation relation. And now they depend on the position on the space. And here, this is not a flat metric, it's a curved metric. And these new Dirac matrix, they are related with the old Dirac matrix with the field. This is basically another formulation of general relativity, or more generally for study differential geometry in curved manifolds. I won't dive into details about that, but you can feel free to ask if you mind. But they are related to the old Dirac matrix, the one we all know from special relativity. And the curved metric will be related to the flat metric by means of the field-line also. So let's make an example to make things more clear. Let's consider we have some graphene sheet with this kind of deformation. It's basically a Gaussian bump here. So, the height of this deformation with relation to the XY plane will be basically this exponential. And we can construct a metric for this surface here. So the first thing we need to do, since it's cylindrical symmetry, we will embed this surface here in the space time. This time is important, we will see. In a space-time with cylindrical coordinates. So basically, we will have this metric here. Of course, we are dealing with a relativistic equation, so we can't forget the time part of the metric. But the height will be just the derivative of the, better say, the z coordinate will be determined just by the derivative of the height of the surface. So in the end, we can substitute the dz here in this form of the metric and obtain the 2D special metric or 3D spacetime metric for this surface here, which will basically have this form here. So this is written in this way because we have this alpha parameter here, which can be used as a perturbative parameter if you want to calculate things like green functions, to calculate the density of state spectrum, etc. But in the end, if we take the Dirac equation, we can calculate the geometrical quantities in there and obtain the Hamiltonian. So here I have the Hamiltonian we obtained for the deformation on the last slide. And here we have a Hamiltonian for a flat sheet of graphene, but now using polar coordinates, okay? So it may be something that looks curved, but indeed it's flat, it's just a coordinate system. So we can see that we have some difference here. The first thing we can see comparing the two Hamiltonians is that we have an effective Fermi velocity in the radial direction. To be more clear, we can factor out this term here, and it will accompany the Fermi velocity, but this is dimensional. So in the end, we are modulating the Fermi velocity in the radial direction. In fact, it will be smaller, more close to the deformation than it is in the plane part of the sheet. And also we can see that we have an effective magnetic field emerging in the system, which will have this form here. And an important thing is that the presence of the curvature in general, which leads to this presence of an effective magnetic field, it induces corrections in the density of states. I think I forgot to put some image, but basically you will have a density of states that's bigger in the region of the bump than outside the bump. And corrections in the density of states will change the transport properties of the system. So more generally, we can think the same way for string fields, for example. The string fields will induce correction in the hopping parameter. It will not be constant anymore, and it will, in fact, depend on the direction you will have. For example, if you make one uniaxial string and make one of the bond directions smaller, this will change the helping parameter in one direction, and the other will remain constant. And we know that we can show actually that this change in the hopping parameter will bring us also an effective gauge field for the low energy. But this effective gauge field has a very interesting feature. Because of the time reversal invariance, these gauge fields will have different signs for each value. So what happens? If you have a real magnetic field, it will break the time reversal symmetry. So, okay, you don't have the symmetry more in the system. But these effective gauge fields, they don't break the time reversal symmetry. And in fact, what happens that they don't break is that they have different signs for each value. So this is interesting. Indeed, we can show that using elasticity theory and some approximations, that the low energy Hamiltonian for the graphene in that case will have this one. So this is reminiscent from the minimal coupling. The difference here is that we also have the valley pseudo spin here. So for one valley, this will be there will be a positive sign here, and for another valley, it will be a negative sign here. And you can imagine that you can also include a real magnetic field here. And the interesting thing is that the real magnetic field and the pseudo-magnetic field will compete with each other. So in one valley, they will sum, and in the other valley, they will cancel each other. So you can play out with these kind of configurations and study some transport properties, for example. But the main form of the gauge field will be this one in terms of the string tensor. So epsilon is just the string tensor, and here UI is the in-plane displacement in the two directions, in the x direction and y direction, and h here is the out-of-plane displacement. So basically, if you have some experimental data with the string data, the string information of your sample, it's very easy to model out this kind of effect. Indeed, an interesting thing, as I said, string fields can cause a lot of effects. And the paper that I am one of the co-authors, the idea was to do this that I just speak, is to make some experimental data for one specific kind of deformation and model out using a tight binding model and study what are the effects that this deformation have. For example, we took the effective gauge field and calculated some quantities. And the main result we obtained is that a periodic string field, which causes a periodic gauge field, it causes an effective, it generates an effective antiferromagnetic honeycomb superlattice. So we have basically a magnetic superlattice, which is honeycomb, and it's an antiferromagnetic kind of magnetic superlattice. And the interesting thing here is that when we consider the spin orbit coupling, we can see that this antiferromagnetic honeycomb, this antiferromagnetism is actually non-collinear. So this is one of the results of the paper we published. There are also a way of tune this magnetism applying electric fields, etc. But aside from what I told during the presentation, There are a lot of other features that you can study in graphene. Basically, it's almost infinite, the number of phenomena that we have, the number of different systems we have. So one of them, it's very interesting and very famous also, is twisted bilayer graphene, which is basically you have two sheets of graphene, one over each other, and you twist one of them with relation to the other. So you are making something like that. And the surprising thing here is that if you twist the two sheets by a very specific angle called magic angle, which is a small angle, but I don't remember exactly what it is, you obtain superconductivity. So very interesting things can happen with graphene, especially when you add interactions to them. Here we discussed only three systems because the interactions makes things way more complicated, and I don't have much experience with that. I have more experience with free systems. And of course, you may guess that it's a lot of topology stuff going on in graphene. Well, when I was discussing the quantum Hall effect, I mentioned the Sher number. The Sher number is a topological invariant, if I'm not mistaken, from the Sher class. And these kind of topological invariants are very important to condensed matter physics at all. There is a research area called topological materials, and graphene is one of them. In fact, I only mentioned the traditional quantum Hall effect, but in graphene you have spin quantum Hall effect, that you have another kind of topological phase without a magnetic field. You have spin polarized currents, basically because of the addition of a term of spin-orbit coupling. You have also valley quantum Hall effect, which means you have the valley, you have Hall current, which is valley polarized. And all of this stuff is related to boundary states that can conduct electric current in the bulk state, state that is an insulator. So this is the whole thing of topology in condensed matter physics. And also it has to do with Barry phases, Barry connections, etc. And one interesting thing, I think it may be the more interesting for you, if I'm not mistaken, most of people here are from high energy physics. There are a lot of models of ADS-CMT correspondence, which is basically ADS-CFT correspondence to condensed matter physics, that have emergent graphene. These kind of low energy behavior of graphene emerging in the condensed and in the field theory side. Some time ago, unfortunately, I don't remember exactly the paper, but I found one paper on ADS-CFT that they find exactly a graphene behavior of the field theory in the boundary of the spacetime. So there is a lot of things in this direction here also. So here are the references I used. If you want, I can send the slides for you, so you can look with more detail. And thank you very much for your attention. If you have questions, please feel free to ask them. And thanks.
Okay, so thank you, Eduardo, for the nice talk. Yeah, we can. Is there any question from the audience?
I have a question, but very general. Somehow, you're emphasizing the use of topology, but as far as I understand, this is always topology in the dual space. What are the topological consequences of the real space? I mean, the the surface where the system is,
okay.
is mounted in, I don't know.
Well,
Or...
this is a good question. In terms of topology, I find it a little bit hard to say because most of the things of topology in condensed matter physics are related with the topology of the bands, of the band structure. So
right.
it's not related to the
Yes.
topology of the real space, but the geometry of the real space has some effects. Actually, I saw some time ago, I can look for it, but there are some...
It's not simply taking care of in the boundary conditions that you impose. If you have a ribbon, for instance, instead of having a sheet, open sheet, you close it and you impose certain boundary conditions, and you may have a torus or whatever. We're not thinking of topology in that sense. I'm very naive. I mean, I've never studied these sort of things.
Okay, let me think of it a little bit. Because the thing with topology, as I said, it's the band structure. So if you make some kind of modification in the real structure of the graphene sheet, you may or may not have a modification of the topology of the band structure. So I think that when you consider a finite system, if you close, for example, the ribbon, you may be causing a change in the band structure because we are basically restoring the periodicity that we didn't have later. So I think this can change, but I can talk with properly.
And in the other language somehow.
Yeah.
Yeah, right.
And I mean, I am not a very specialist in the topology thing here also. I know the basics. As I said, I am not a very specialist in condensed matter theory. I know some things.
No, this question was more along the line of what you were doing of thinking of a system in a curved space.
Mm-hmm.
Because for me, curved space is there are topological considerations somehow as well. But okay, we can discuss later.
No, it's an interesting question because I know there are some models. Okay, are models, not realistic models, but there are some models for graphene that can emulate black holes, for example. So in the end, you need to have some kind of topological effect, like a hole in the graphene, so that you can model the black hole. So you have some kind of event horizon. You can study things like Hawking radiation.
Right.
I never studied this in detail. I just saw some papers and I read, but it's more complicated than it looks.
So I have a question, also nice because I'm not. Also two questions. First, this Dirac cones is a particular property of graphene, or you can model this in other two-dimensional materials?
No, it's present in other kind of materials. There are a lot of graphene-like materials, which are basically elements of the same group of carbon that you can construct some 2D structures with them, and they present Dirac cones. There are even materials that are not bidimensional that have Dirac cones, if I'm not mistaken. Okay. They are not exclusive from graphene. Maybe graphene is the most famous example, but they exist.
And second, why do you use or do you see massless fermions instead of massive? Because you observe quantum Hall effect, right?
So, okay. In quantum Hall effect, for the traditional quantum Hall effect, we don't need a mass term. But when we'll talk about spin quantum Hall effect, for example, you need to add another term related to the spin coupling that ends up being a mass term. So then you have a gap open in the band.
Okay.
So you can add mass terms to the system. It's just the pristine behavior of graphene don't have mass.
Yeah, okay. So it's more like photon interaction instead of electron.
Yes.
Okay, so if there are no more questions, Danilo was asking if you can send the references. To put it on.
Or at least to
To
show
flash.
the slide
Yes,
where
yes.
the references are. Maybe
No,
to
I
take
can
it.
send them.
Okay, thank you. So we can send.
I will send you later.
Yeah, thanks. So let's thank Eduardo.
Mauro have a question.
Yes, thank you. So I have a comment complementing Felipe's question, and then I have a question. Besides, as Eduardo was mentioning, that there are other materials with Dirac cones, the fact that they are describing massless particles basically is the linear dispersion relation, the fact that there is no gap. E as a function of momentum is proportional to it. So the fact that there is not a constant term for 0k tells you that it's a massless particle, right? And that applies, I mean, not only for linear dispersion, but also for a paraboloid dispersion relation. Like when there is no gap, meaning energy value different from 0 when k is 0, then it's massless, right?
Yeah, right.
But in this case, it's not only massless, but also linear. So it's massless relativistic, like, right, Eduardo?
Yes, yes.
And my question, Eduardo, was regarding these two singular points in the Brillouin zone. You mentioned this K and K prime. And when you showed the Dirac cones in terms of the these valence sigma matrix like and the spin sigma matrix like, you showed that the K and K prime, they had the tau values switched. There was this slide where you had the, you passed it, I think.
Here?
No, it was a slide where you had the two cones for at the K and K prime points, and you showed the values of I don't remember it was whether it was lambda or tau. There, you had, right, sorry, it was eta, it was not. So in this graph, eta is the chirality, right?
Yes.
And right, so the conduction band.
The conduction band is this upper band,
Right.
which has lambda equals plus, plus 1.
So my question is, why are the helicities in the conduction and valence band interchanged for the K and K prime?
So, well, the thing is that the conduction band, it has to be the plus sign, and the valence band needs to be the minus sign. This is how we model them. We choose that the band index will be in this way, right?
Right. So lambda is the band index. So that's a
Yes.
label for conduction and valence. Yes, that
Yes.
I get. I guess my question was more regarding the chirality. Or
Okay. So what we have here, writing the Hamiltonian in terms of the chirality operator, we find this energy spectrum, right?
okay.
And the other energy spectrum we have for the Hamiltonian, is writing it in the normal way, is that one here. Okay, so comparing these two spectrum, we can see that lambda is equal to the valley index, which is tau, and the chirality. Okay. So, for example, if I am in the conduction band, this needs to be +1. And well, let's suppose that I am in the K valley. So we know that this is, the tau is +1 also. So consequently, eta needs to be +1 in order to this be +1. The situation changes if we go to the K prime valley. In that case, the tau will be -1, and consequently, the chirality needs to be -1 also, so that the lambda be +1.
Oh, I see. I see. So it was rather trivial. It's just due to the fact that the K and K prime points are
Yes.
labeled by different tau values. Okay, yes. Such that the product is consistent with the band in which you are. Okay, thank you very much.
Yes. You're welcome.
Can I follow up on that question? So is it also related to the fact that K prime and K are related by time reversal or something like that? Because I believe that if you apply time reversal, you go from K to K prime.
Yes, yes.
And then you can change sigma to minus sigma because it's like a
Yes, exactly.
magnetic field. Yeah.
More questions?
So, by the way, one more quick question. So, I missed that step when you get the flat Hamiltonian. So, is it that you're replacing?
Here?
Yeah, that one.
Okay.
I've never seen that Hamiltonian before. I mean, is it that you replace K, the K operator in the real space? It's like when you, like usually in quantum mechanics, P equals.
No, it's different. Basically, what I'm doing, this is, you can think of this form for the Dirac equation as an equation which is suitable for an arbitrary coordinate system. Okay, so I'm just applying polar coordinates in this equation, calculating the geometrical quantities, and then I can see that the Hamiltonian takes this form.
I see, but then what is the connection of this Hamiltonian or the previous one with the graphene Hamiltonian in K-space? Is it just it's the same equation, but
Yeah.
One is in momentum space and the other one is in real space.
No, the other one was in momentum space. This is the in real space. Maybe it's something that I should have stressed better. But the other one is in momentum space, such that if you change, for example, here, if you change K is just a momentum variable, so you can change it by a derivative.
I see. But at that point, you assume that the graphene is like a sheet, right? I mean, there is no more atoms and
Yes. One thing, when we make this expansion here, we are basically taking the continuous limit.
Yeah.
Right.
Okay.
And this continuous limit is, in fact, the low energy limit.
I see. Yeah, that makes sense. It's like a wave equation. Okay.
Yes.
Awesome. Thank you. Very nice talk. Thank you.
Thanks.
Are there any other questions? If not, we can say thanks, Eduardo, again.
Thank you very much for the talk. It was really clear.
Thank you guys for attending. So hope to see you.
We'll be in touch, Eduardo. So